addressing. And again, I do skip some slides that are in the full PowerPoint that's in Canvas. So if there's anything, some of them I skip because I'm looking at them, I don't even know what they're trying to tell us. So sometimes, you know, the people that make PowerPoints, and I found especially with Medicat, is they sometimes throw up a graphic or something or a table, and with no explanatory text, it really doesn't say much. But mostly I just hid slides that are elementary stuff that you should, you know, that I don't even think is worth reviewing. But I didn't, you know, we're going to review IP addressing, but we're just not going to spend as much time on standard addressing, just the basics as CNT140 does, because that's where you presumably first learned it. Okay, so network and host portions, everyone should know that. In a classful address or any IP address that has all 255s and zeros, or just 255s and zeros in the subnet mask, will have the network ID and the host ID will be on octet boundaries. So example, this one, presuming a standard class C subnet mask, the first three octets are network ID 255.255.255. .0 is the subnet mask, and then the last entire octet is the host portion. And that works, you know, a lot for a lot of situations where you don't need to break up the network and host portion or change it in any way, where, you know, it works to do it on octet boundaries, but not always. And so that's why you need to subnet, be able to subnet. So one of the things that you need to start, you know, kind of getting into your head about IP addresses and subnet masks is the number that the subnet mask determines how many bits of the network ID, how many bits of the IP address are network ID, and how many bits of the address are host ID. Not necessarily on octet boundaries. So when you have a subnet mask of 255.255.255.240, all right, that means 28 bits are network ID, and the last 4 bits are the host portion of the address. And so that's kind of what you have to start, the way you have to start thinking about IP addresses with their subnet mask, or really even not so much the subnet mask, although subnet mask matters. That's the way you usually express an IP address when you're assigning it to a host. But really, if you can take that subnet mask and turn it into CIDR notation fairly quickly and easily, that's easier. You see at a glance how many bits are the network ID. You know, the slash number, whatever comes after the slash, is the number of network ID bits. And the remainder bits are the host. So if you see a slash 24 bits network ID, 8 bits host. If you see a slash 22 bits network ID, remaining 10 bits are host. Okay. So the network and host portions are determined by the computer by doing the binary AND process, right? So we can just look at this, especially when it's on octet boundaries, and we see, okay, everywhere there's a 255, that means that octet, that entire octet is part of the network ID. And anywhere there's a 0 in the subnet mask, that entire octet of the IP address is part of the host. Computer doesn't reason like that. It doesn't look at 255s and zeros and stuff. It obviously just looks at bits. So what it does is it takes the binary of the subnet mask and the binary of the IP address for each octet and does a binary AND. And when that process is done, out falls the network ID. So when it's done in this particular case, you'll get 192.168.10. And since ANDing anything with all zeros is going to yield 0, then .0 will end up being the fourth octet, which means it's the network ID, right? So anytime the entire host, anytime you see a IP address along with its subnet mask, and the entire host portion of the address is zeros, that means it is the network ID. It's not, you can't actually assign that address to a computer. You can't assign the network ID to a computer. And what's the other special address when the entire host field is what?
The broadcast at the end.
And that's when the entire host field is what?
255.
Not necessarily 255. Put that in binary.
Ones.
All binary ones, right? Because it could be 248 could be, or I mean, it could be 7, right? 7 is the last 3 bits. And if the host is only 3 bits and it's 111, then the broadcast value of the broadcast address is simply 7. So that, that's what you have to remember. It's all the host bits being 1 or all the host bits being 0, not necessarily an entire octet full of them. And, and that is all dependent on the subnet mask / prefix. So when I say prefix or CIDR notation or / notation, it all means the same thing. Prefix is what the term is used strictly in IPv6. So in an IPv6 address, there is no such thing as a subnet mask. It'll be, a IPv6 address of some sort or a bunch of hex values / the number of bits that represent the network, and then remaining bits are host. So prefix is a term I frequently use even in IPv4, but it's also called CIDR notation or / notation. Okay, so speaking of prefixes, so if we have, well, basically, it's not a bad idea to get just familiar with looking at an IP address or a subnet mask, I should say, and automatically knowing what that looks like in terms of the prefix length or prefix value, right? All your classful addresses or classful subnet masks are 8, 16, or 24. But then you've beyond 24 bits, you just, start adding ones, 25, 26, 27, 28, 29, and 30. We stop at 30 because why? Why can't we have a subnet mask when we're assigning an address to a host? Why can't we have a subnet mask of 31 bits?
You need 2 for the network ID and the broadcast.
Right, you need at least 2 bits because 2 bits gives you a total of 4 addresses, right? Well, because 2 squared, right? But 2 of those are going to be used, reserved, let's say, for the network ID, and the other one is reserved for the broadcast. So that gives you only 2 addresses left when it's a /30. If you went to /31 in the subnet mask, you'd have 1 bit left. And yeah, the 2 addresses would be the broadcast and the host, or the broadcast and the network ID. So there would be no addresses left for host. Okay, so This is just showing you, starting with /25, this is just showing you additional prefixes when you're starting with /24, 255, 255, 2550. You can also have /17, 18, 19, 20. They're not in this table and make the table really long, but those are possible slash numbers too. And so with the /17, for example, you'd have 255, 255, 128. And for /18, you'd have 255, 255, 192, and so forth and so on. And same thing here, you could have a /9, which would make it 255.128, a /10, 255.192, and so forth, all the way up to /15. Okay, these are the ones that, we, at least in the easier for most people, subnetting problems just deal with the fourth octet. But we'll have plenty of problems that deal with the third, and maybe one or two that deal with the second octet as far as the subnetting part of the problem goes. Okay, so remember what a binary AND is and how it, it's called subnet mask because what it's doing, the subnet mask is masking out the host portion of the address. It's letting the network ID, so this IP address 192.168.10.10, and with a /24, which is what this is doing, or 255, 255, 2550, the zeros mask out the host portion of the address so that what falls through when you do a binary AND is just the network ID. And that's why it's called a mask. The purpose of, the reason that they call it mask, subnet mask. Because 255 means all ones, right? So anywhere there's a 1 in the subnet mask, the only way that there will be a 1 result is if there's a corresponding 1 in the IP address in that same location. So with binary ANDing, only 1 and 1 makes 1. It's like multiplication. Really, that's a good way to look at binary ANDing is multiplication. 1 times 1 equals 1. 1 times 0 is equal to 0. 0 times 1 is equal to 0. 0 times 0 is equal to 0. So the only way that you get a 1 when you do a binary AND is if both bits are 1 in both the IP address and subnet mask in that location. All right, so yeah, masking is something that it's not just something you do in networking. If you're going to be in programming or something, a lot of times you have to get to the value of a particular bit. So you'll mask off all the other bits by putting zeros in the locations of the other bits, except for the one that you want, in which case you'll have a 1 in that location. And then when you do the ANDing between the two values, you would just get the value of that 1 bit. So it's not just in networking and subnet masking that you deal with binary ANDs. We'll do, for those of you that are taking CNT140 in the spring, we get into that eventually, doing some binary operations in Python. Matter of fact, we do some binary operations and do a little bit of subnetting. I wrote a subnet calculator in Python, and so I just show you some of that. You don't actually write the entire calculator, but you do some of the stuff that would be required for it. Okay, so 3 types of addresses. In the subnetting problems, in that one table of problems, you had to find 2 of these addresses. You had to find the network ID and the broadcast address for a given IP address along with its prefix or subnet mask. So you've got the network ID, network address, which is the host when the host portion is all binary zeros. The broadcast address when the host portion is all binary ones. And then everything in between are host addresses. So the very first host address on any subnet will be where all the host bits are 0 except for the rightmost, which is the 1 bit. So in all subnetting problems, when you're trying to figure out, okay, what's the address of the first host? That's usually what we ask you. What's the address of the first host and the address of the last host in that subnet? So to figure it out, you just take your host portion, all zeros, and then the rightmost is a 1. For the last host, all the bits are 1, except for the last one, which is a 0. Because if you made the last one a 1, it would be the broadcast. Yeah.
The 4 addresses or the 3, we need 2 bits for 3 addresses, correct?
2 bits gives you 4.
4 addresses, but we need them for 3, right?
You need, no,
For the network address, the broadcast address.
yeah, we just have to exclude when we need 2 bits because we need at least 2 bits in the host because we have to exclude always the network ID and the broadcast address in terms of the usable addresses to assign to a computer.
Can we do that with 1 bit?
If you only have 1 host bit, then you only have 2 addresses, and one of them is the network and one of them is the broadcast.
Oh, so one's the computer address?
Well, you need, yeah, if you're going to create a subnet, can you guys in Zoom hear me?
I think you're cutting in and out, but we lost the video. We can see the shared screen, but the camera's off.
Oh, really? Huh.
Just happened a second ago.
Okay.
I understand.
Yeah. So you can't see any video, but you can see the shared screen. Is that what you said?
That
Yeah,
is
that's right.
correct.
See, yeah, just my still pictures.
Yeah. Yep.
Okay, yeah, I don't know what's going on with that. Maybe I need to reset the camera. I'll do that at a break. But as long as you can see the shared screen, that should be the most important part. Okay, I hope that works for you.
Yeah. If it
Okay.
changes or something, we'll let you know.
All right. Yeah, that's. Okay, public and private, you learned about that in CNT 101. The entire 10 address, when 10 is the first octet, all 2 to the 24th addresses are private. So the entire, anything starting with 10 is considered a private address. Anything starting with 172.16 through 172.31 is a private address. And anything starting with 192.168 is a private address. So private address means that, like specifically, what does that mean? What can't you do with a private address?
The internet.
Yeah, it can't be routed onto the internet. Okay, routers are supposed to, as long as somebody configures them correctly. The router that is outgoing to your ISP should have some rules in there that will drop any packets that for some reason are not public addresses. If they have a private address, either, well, primarily in the source, but they really shouldn't have it in the destination either. But the most important thing is that you don't let any source addresses out onto the internet that are private addresses. So your router that connects to your internet provider should have rules that will drop those packets that might have a private address in the source. And you could probably write rules for dropping them if they're in the destination as well. In the project class for the degree program, that's one of the last things you do in the project is configure the router to drop private addresses before they go out to the internet, just in case they were to go out to the internet. Okay, but other than that, private addresses are fully routable inside an internetwork, inside a company's private network. So they're fully functional except for going out onto the internet. And of course, the reason for that is the lack of IPv4 addresses. There's so many computers out there that need to access the internet or want to access the internet. There was, would have run out of addresses long ago, but anybody in the world can use a private address to do all of their configuring of their internal network, as long as they, if they want access to the internet, then they have to do network address translation on the outgoing router. So that network address translation is where the private address gets turned into a public address or translated to a public address. Let's say replaced with a public address before it goes out to the internet. So I've got a animation for that. All right, so this demonstrates how NAT works, more specifically PAT or port address translation, but which is just let's say a superset of NAT. Okay, I don't have sound again. See if that did it. Tell you would think that the technology for microphones and cameras is pretty darn mature, that we wouldn't have these problems with the mics and the cameras. Let's see. Oh, somehow the video just stopped by itself. So, see if it's a different. Hello, hello. Okay, I can hear that. Okay, so let's see if this works. All right, well, you'll have to read it. So, I don't know why the audio is turned all the way up. Let me make sure it's not muted somehow. Did it stop?
Yeah.
Yeah, sure did. Give commentary as this goes along. All right, so computer one is going to communicate with web server one. So it puts the destination IP address for web server one in the packet header, and in the transport layer, port 80, assuming that it's not, a HTTPS communication. And then the source address of the computer, which is a private address, 192.168.1.101, goes in the source part of the header, and the source port goes in the TCP header. So a lot of times IP address and port are just shown with the IP address, a colon, and then the port number. So that's how the packet leaves the computer. And when it gets to the router connected to the internet, the router will see that it's a private address, and it will perform a network address translation on it. So in a small home office type router, what will typically happen is that the router will use the IP address that it was assigned by the internet provider. In other words, its outgoing interface IP address. It will use that as the address to do the translation. So it puts the entry in its NAT table, basically saying that a TCP communication coming from internal address 1.192.1.101, port 3569, has been translated to 24.116.23.11. And it uses the same port number, but that isn't a necessity. In other words, in a large network, that port number could potentially already have been used in the NAT table, in which case it would use a random port number for the public address translation. So now the packet, once it changes it, Now the packet is suitable to go out onto the internet. So the web server receives it, it replies to the 24 whatever address. And the reverse happens when the reply comes. So the router gets the reply packet, sees the destination, 24.116.23.11:3569, looks in its NAT table and sees that, oh, I need to swap out that address with the private address to deliver it to the internal device. So the translation of the communication between computer one and that web server will use the same entry in the NAT table. And then, you know, as other devices communicate with the outside world, the NAT table, you know, entries are added. You'll see, so if another computer wants to communicate with some other device or even the same device, a new entry is created in the NAT table. And the only thing that's different in the public address part is the port number. And that's how each entry, even though they're using the same IP address, that port number differentiates the communication. And so this, when a return packet comes for this IP address and that port number, then he knows to use 1.102 in the translation for the incoming packet. Every web application or even every window or tab that you open on a web browser or any other web-based application will have a different port number assigned to it. Basically random value. Since a port number is 16 bits, the port number could be anywhere between, well, let's see, up to 1024 is reserved. So 1020 or up to 1023. So up from 1024 to 65535. So any one computer could have that many translations, not very, or that many internet-based applications. Not very likely, you'd probably run out of memory before you got that many, but that would be the most that any one device could handle. All right, so that's NAT.
Before we move on to.
Yeah.
So that translation is necessary because there's no more IPv4 addresses, right?
Right.
But
That was one of the main reasons that NAT was developed, was because of the lack of IPv4 address.
right, but isn't NAT just giving it another IPv4 address? Like I don't understand.
Yeah, but it's using the same address for potentially hundreds or thousands of devices.
It's just switching the port number.
Only the port number was changed. So in those translations, that one address was used over and over again. Just the port number was different. Yeah. And then other protocols that don't have port numbers, like really the other most common one that might be used to go out on the internet would be ICMP. There is a value in ICMP. I can't remember what the field is called, but something that is similar to a port number that NAT uses in lieu of the port number. So a protocol that doesn't have some sort of identifier for each packet or each conversation would be able to be NATed. But but the most common, you know, we either use TCP or UDP. They both use port numbers, or we use, you know, low level like ICMP, but there's really nothing in between. There's nothing else that goes out on the internet.
ICMP is a broadcast, right?
No, doesn't have to be. No, ping is not a broadcast. So you can ping address, you know, any internet address and it'll work and it will get translated on the router. Okay, so that's NAT. Loopback address is reserved, as you know. And then there's one other range of addresses that's reserved, and that's the APIPA. That's reserved when a device is trying to get a DHCP assigned address and there's no DHCP server listening. So it will self-assign a APIPA address. So these are addresses you cannot use to assign to a computer. You can't just give or let's say you shouldn't. You might be able to get away with it, depends on the error checking that Windows does. But you shouldn't use 169.254 on anything to statically assign to a device. And of course, 127 wouldn't be useful either. Nobody can access it from the outside world. Okay, you know the class A, B, C, and D. Hopefully those ranges are starting to stick. And again, you know, that's why that's class full, and class list means we can assign any subnet mask we want. We don't have to use the class full subnet mask. Okay, so network segmentation. Network segmentation really means subnetting, or at least that in the context that we're going to be using. And subnetting means, or another term for subnetting is to break up your network into smaller pieces. So what are some of the reasons we'd want to segment our network or subnet our network?
Network traffic.
Okay, so to do what with network traffic?
No, we have a lot of broadcasts.
Broadcasts are, yes, exactly. Broadcasts are a big problem in modern networks because devices are just continually spewing out broadcasts or multicast, which in most networks are treated the same as broadcasts, at least by the switches.
It's troubleshooting too, wouldn't it?
And troubleshooting would be, if you have fewer devices that you are having to sort through to find some offending packet types or something. If you're capturing packets with Wireshark and there's 1,000 computers, then you're going to get a lot of packets that you may not want. If there's 50 computers, that's a lot more manageable. What are some other reasons besides troubleshooting and let's say broadcast containment?
Just having available addresses.
Subnetting, yes and no. Now, remember, whenever you subnet, each subnet, with a class C, there's one broadcast and one network ID, right? And 254 usable addresses. If you create 16 subnets from that class C, each of those subnets has a broadcast and a network ID.
You've actually
So
cut down
in that case, you're reducing your total available addresses to assign to a host. But usually that's not a good enough reason to not subnet. But I just wanted to point that out, that you lose addresses when you subnet because each subnet has to have a broadcast and a network ID, which can't be used to assign to hosts. But to your point, the other, it does save addresses in the sense that I'll give the example when I was I was the IT director of a community college in North Carolina before I came here. And we were assigned, this was in the late 90s. Late 90s. And we were assigned by the state a couple of class C public addresses. And at the time, people just didn't know why, they didn't know that we needed to conserve addresses. So we got these two class C addresses. So we had 508 addresses. Well, the devices that were facing the public internet, a router, like a web server, DNS, there was like three, okay? We didn't need 500 addresses. Because, well, first off, we were first using a gateway device because we were on Novell NetWare using IPX. So we didn't, a gateway device just translated IPX to IP for us. But later on, when we got rid of IPX, we were using private addresses in that. And so we just had a handful, let's say, of addresses that needed to be facing the outside world that could be accessed by the outside world, web servers, DNS servers, routers. So at the time, that's what you did though. You gave them an entire class full address, usually a class C. Well, after, by a couple years later, state came back and said, we see you're only using, so many addresses. So they took back one of the class Cs and then they just gave us like a /28 for the other class C. In other words, they kept, 4 of those bits for other institutions that they needed to give addresses to. So, they didn't, at the time, like I said, the internet was still, even the late 90s wasn't like it is today by any stretch. And no one thought there was a problem with numbers of IP addresses. So in that sense, especially when it comes to public addresses being assigned by ISPs, conservation of addresses is huge. And that's why you would subnet. They're not going to give a company a class C unless they're a really big company that needs 500 or 254 public facing devices. Usually give them a /28 if they need, 14 or so devices, or /26 if they need 60 some public facing devices, whatever.
Only devices that need a host ID.
Yeah, any device that needs a host ID is what I mean. Yeah, like any device that will be accessed by an IP address.
Okay.
Needs from the outside world.
Yeah.
Now there is a way to use NAT to take a public address and translate to a private address and allow, access to the outside world, but that's not done very commonly. Usually your devices that you want the external world to access, you put in your DMZ and you give them a public address. Because doing translation from public to private it doesn't work that great for certain applications. Okay, so broadcast domains, we talked about that. That's one of the reasons you subnet. If you had a class B address, let's say you had 1,000 computers, and let's say, forget about NAT for the moment, but let's say you had 1,000 computers. Forget about accessing the internet at all. If you had 1,000 desktop machines in your network, in your organization, and you had a class B address and you couldn't subnet, then all of those computers would be on the same network, the same broadcast domain. So that means that any computer that sends a broadcast in the entire network, all 999 other computers are going to have to hear that broadcast. And you've got 1,000 computers that are regularly sending broadcasts. And so when you have that number of computers, especially client machines like Windows that is very chatty and sends lots of broadcasts and multicasts, your devices are going to be overwhelmed with just serving, reading the broadcasts, and 99.9% of them aren't going to be for that computer. So they're just going to throw the packet away. So you want to take that 1,000 computers and break it up into smaller broadcast domains, which means subnetting it, which means having a router interface for each of your subnets. So routers stop broadcasts. Any broadcast that occurs in this network, there was, let's say, a couple hundred hosts in here, the broadcast would be heard by all the devices connected to these switches, but when it got to the router, he wouldn't forward it. It wouldn't go out here, right? Good, which is a good thing. If it went out to the internet and routers forwarded broadcasts, then the internet wouldn't work. So one of the things that's worse about broadcasts than just a unicast that gets delivered, to the wrong device is a unicast frame that gets delivered for whatever reason. You're using a hub, which, everything goes everywhere, or the switch doesn't know the address yet, the MAC address, and so it floods it out all ports. Well, when it's a unicast, the NIC will see the destination MAC address, and if doesn't match its own MAC address, it just throws it out. But if it's a broadcast, it has to send it up to the upper layers because it doesn't know if that broadcast is important or not to that computer. So it has to send it to the upper layers, which causes an interrupt in the computer. Everybody stops what they're doing, reads the packet, and sees if something has to happen with that packet. And you get enough of those happening at one time, and the computer just does nothing but service broadcasts. I've seen that happen, a broadcast storm, where as soon as somebody made a connection in the network that caused this broadcast storm, every computer in the entire network just froze, within a second, because the broadcast storm happened so quickly, and it was just thousands and thousands of broadcasts suddenly being thrown out onto the network. And back then it was Windows 98 or something. It couldn't handle, that level of broadcast. Even today's computers would have a hard time. All right, so large broadcast domains, we need to segment them into smaller. The rule of nowadays, they say, if you can keep your broadcast domain under, 50 or so, that's awesome. But if you go 100, 150 computers, that's probably not too big of a problem because the processors are fast, the switches are fast today, that it's not going to be too big of a deal. In this case, they're making it 200, which is probably still usable, but I would be worried about the number of broadcasts being generated. Another reason for segmenting networks is to divide up your users by location. So every floor of a building, or depending on the size, each building gets a separate subnet. Dividing things up by function, like department. So each department gets their own subnet, and less commonly, or let's say used in conjunction with one of these other two, might be device type. The most common thing when you're subnetting by device type is put all your servers in a data center in their own subnet.
So with the device type, could you possibly segment wireless, phones to their own number?
That's very common too, yeah, to have your wireless devices on their own subnet. We do. All of our wireless devices are on a separate subnet. So when you connect, they're on their own subnet and they get routed to wherever they need to go. And one of the reasons that you might do it by group or function is security purposes. You can create security rules on the router, on each interface of the router, to say, okay, administration can access anywhere, but students can only access, students, they can only access their own subnet. So you could essentially put a rule on router 1 that blocks the student network from accessing these other departmental subnets. Most likely you'd let them, of course, access the internet, and then you might have student servers or something that they could also access as in another subnet. But security is another possible reason you would subnet. So we, in this department, when we subnetted our network couple years ago, we used to just be 172.31/16, but we started to get so many servers and with all the virtual machines and everything, we decided to subnet. We basically did it by function. All of the servers that belong to VLab are on their own subnet. All the ones that belong to the cyber range related stuff are on their own subnet. The classrooms, the 2 classrooms are on their own subnet. So, and there's a few others, but those are the main ones. All right, so we'll talk about subnetting. So octet boundary subnetting is the easiest thing. It's the most straightforward thing to do. And it's good to do an example of that. So I'll bring up the whiteboard. So I'm just gonna blank whiteboard since this is pretty basic. So. Okay, so if I am starting with a so if I'm starting with 172.16, let's say, .0.0/16. Okay, the most straightforward way, so that's a big, class B, if I've got 1,000 computers, I don't want to put them all in that one broadcast domain. So the easiest thing is, okay, let's say I can have up to 250 computers on each subnet. So the easiest thing to do, especially since when you're using private addresses are plentiful. So it doesn't matter if I waste some addresses. I'm in this particular example, I'm only doing this for broadcast containment to keep my broadcast domains down. So I can basically do this 0.0/24. Now, by changing my /16 to a 24, I get how many subnets? Like I had this whole address space, 172, this whole 172.16.00/16 subnet or network. I just changed it to a /24. How many subnets can I create?
256.
256, right. 8 bits. I reallocated. I know that a lot of the terminology, including the Cisco, will say borrowing bits. I never liked the term because you never give them back. So it's like you're reallocating those bits from being part of the network ID to now being part of the host ID, or actually from the host to the network in this case. So what are those subnets? Well, the first one is always our original network, 172.16.00, except it's got a /24, which means our host is only in that 4th octet. Our next subnet is 172.16.1.0. And you can guess, I'm not going to write all these numbers, 2.0 and 3.0. All the way to what?
255.
255. Dot 255.0. So those are the 256 subnets from 0 to 255 that I can create by just taking that /16 and saying, all right, it's now a /24. And I've got the because remember 255 /16 looks like this. So this is where it's good to, see the subnet mask. 255.255.255.0.0. So the first two octets are network, the last two are host. But with a /24, so I changed, so now where I added the bits is where my subnetting occurs. Okay, so that's where your subnetting occurs, is where you added the bits from being host bits to now network bits. So basically by taking that entire third octet and saying it's now part of the network ID, I've got all the values that this third octet can represent for my third octet in my IP addresses. And they're all separate subnets. Again, 0 through 255. So
Cider notation always represent the subnet.
what's that?
That cider notation always represent, is that you only gonna see that when you're.
Yeah, the cider notation or prefix notation, you should always be able to translate that into a subnet mask.
So what if the first one, the 16, let's say it went from an 8 to a 16, and with the first address be 172, would it go on from, instead of 172.16.0.0 would be 172.17? Or that would you add one? to-
So if it started off as a /8 and I made it into a /16, yeah, then it would go from 172. So it wouldn't be 172.16 because this in that with a /8, the second octet isn't part of the network ID. The second octet is part of the host. So with the /8, I would have 172.0.0.0.
Right.
Or it'll always start.
And then if I
at-
made it /16, it would be then 172.1.0.0, 172.2.0.0. So I'd have all the way, I would be able to count from that with that second octet from 0 to 255. And those are my 256 subnets. Because if I start with /8 and I go to /16, then now I'm subnetting with the second octet.
Can you start with, will it ever start, what if it's like /19, it could start that way?
You could start with a /19, yes.
Where the first address would be, so like.
Yeah, well, we'll do that. We'll actually do that when we get into VLSM. We'll start with something that isn't on an octet boundary. Okay, so supposed to be, I did it earlier, what the heck? Where I was able to just clear the whole screen. Shift F10, I was pretty sure. Ah. Okay, I don't know what the heck happened to it then. I'll just create a new whiteboard where I can, it'll take forever. All right, so that doing the subnetting on octet boundary is is easiest and most straightforward. And if that's what your situation allows, then that's what I recommend you do. What we kind of, the way that we teach subnetting in here is that, subnet to conserve addresses. And so people, when they, actually apply this, they're tempted to let's say, make things more complicated than they need to by over subnetting. Now, for the problems that we're gonna do, you're gonna have to subnet according to the problem. But in real life, or let's say a facsimile of real life, which is our networking project. You've got this private IP address range, and you can subnet it however you want. And the way that the network is laid out, you could just use, it's a /16 and you could just use a /24. A lot of people end up doing like /26, they do a VLSM. And I'm like, well, that's great, but you just made it your life harder. There's no reason to subnet, like over subnet if addresses are plentiful. If you don't need to conserve addresses, then don't. Just subnet according to your particular situation and make it as easy on yourself as possible. But there will be times, like if you're an ISP or if you've got a limited address range and you have to conserve addresses, where you're going to have to use the most efficient subnet mask for the number of hosts that you have. All right, let's look at, so that's what this basically did. It's saying, easy subnetting on an octet boundary going from a /8 to a /16. You get the entire second octet to create your network IDs in, and the third and fourth octet for all your hosts. If you go from a /16 to a /24, then you've got the entire third octet to do your subnets addresses and the fourth octet for your hosts. And so that's pretty common, going from a /16 to a /24. When we subnetted ours, we probably could have done that because we had a /16 and 172.31/16. And we did it for a lot of it, but we actually do variable length subnet masks because it seemed to fit our situation a little bit better. But where we could, we just did a plain old /24 for the subnet. Okay, so if you're starting with a /24, these are the possible prefixes and subnet masks that you could use depending on how many networks you need in combination with how many hosts you need on each of those networks. So just remember, for every bit that you reallocate from the host ID to the network ID, for every bit, you are doubling the number of networks, or subnets, however you want to look at it, and halving the number of hosts per network. So you start off with 254 in a class C. When you borrow or reallocate one bit, making it /25, which comes out to 255.128, then you get two subnets, but half the hosts per subnet, a little less than half, because again, now you have two broadcasts IDs and two network IDs, one for each subnet. And then 2 bits, you got double again the subnets. So we went from 2 subnets to now 4 subnets by borrowing and reallocating another bit. And since our host bits is now decreased to 6, we only get 62 hosts per subnet, and so forth. And the largest prefix you can have on a subnet would be /30, leaving you 2 host bits, but only 2 hosts can be assigned because the broadcast and the network are reserved. But you got 64 subnets, so you can create a whole bunch of subnets with that /30, but that are very, really small with only 2 hosts per. So /30, where there's only 2 hosts, where do you think what type of network would those likely be used for?
Nerd basement.
What's that?
Nerd basement.
How about a real type of network?
Well, that's offensive. Yeah, somebody's like personal project or.
How about my network? Here's the pin. Okay, so here's my network. Oh, nice. Changed it into an actual decent, almost a circle. There's a LAN. Okay, so this LAN might have a bunch of hosts on it, so a /30 prefix isn't going to work for the LANs and most likely. But what about this network? How many addresses do I need for that network?
2.
Just 2, 1 for each router interface. So that's where you're going to find a /30. And so typically in most, like the public internet, router to router connections are going to use /30s. And even in large internetworks, private internetworks, if they need to conserve addresses, they'll assign their WAN, wide area network interfaces, with /30s, because you just need 2 addresses and no sense in wasting them if addresses are tight. All right, so that's about the only place, a point-to-point network is what that would be referred to. All right, so this is giving, I don't like too much tables that have a lot of numbers because most people's eyes just glaze over when they're seeing all this stuff. But if tables help you, then use them or study them. I don't, it might be, kind of useful to just see the patterns. And the values for the in this case the 3rd octet of the subnet mask, the values will always be, well, the first possible value is 0. That's when it's /16 is not subnetted, 255.255.0.0. But as soon as you start subnetting, these are all the possible values for a subnetted /16 up to /24, and then the 4th octet repeats the same pattern. So those values, 128, 192, 224, 240, 248, 252, 254, and of course 255, those are the numbers you can see over and over as part of a subnet mask. And if it's not a 255, anything less than a 255 will always be the last non-zero value. In other words, you'll never see 255.252.255. Okay, that's illegal. Because a subnet mask is always going to be binary 1s followed by binary 0s. There'll never be 0s and 1s intermixed. There'll always be 1s followed by 0s. Basically, a /8 is 8 1s. That's the smallest subnet mask. So /8 followed by 24 zeros up to 30 1s followed by 2 zeros. That's the entire range of bits that you can have in a subnet mask. Okay, so a /16 can obviously be subnetted, by borrowing up to 14 bits, or reallocating up to 14 bits. And each bit that is reallocated doubles the number of subnets, until if you go all the way to /30, you get 16,000 subnets. with only 2 hosts per subnet. Okay, so if you have a 172.16.00/16 and it needs at least 100 subnets, then it's going to, first thing you need to do is determine how many bits do I need to make 100 subnets. Because if you need 100 subnets, then you're going to need, to reallocate the number of bits that'll give you 100 or more without going too far over. So that's going to be what? 7. 2 to the 7th is 128. 2 to the 6th is 64, which isn't enough. So you're going to reallocate 7 bits. So your new prefix will be what? 172.16.00/16 was the original. What's the new prefix if you're going to get that 100 plus subnets? Well, if it's /17, that only gives you 2 subnets. That's only 1 bit. So to get 100 subnets, you need 7 bits. So you're going to add that 7 to your 23. 16 plus 7 is 23. So you always take whatever your starting point is, your starting prefix, in this case /16. How many bits do I need for the number of subnets that our organization requires? In this case, 7. So now our new prefix is going to be 16 plus 7 or 23. You're basically adding 7 bits to the network ID. It was 16 bits, now it's 23 bits long. It gives you more than 100 because everything's going to be on, powers of 2. So you get the closest value that meets your requirement. You can't necessarily be exact. So with the /23, how many host bits do you have left?
9.
Yeah, 9. Because if 23 is your prefix, your new prefix, you have 9 bits left.
How many addresses does that give you?
2 to the 9th. So 2 to the 7th is 128, 2 to the 8th is 256, 2 to the 9th is 512, minus 2, so 510. So in this scenario, 100 subnets, well, you can make 128 subnets. Each subnet can have 2 to the 9th or 510 hosts per subnet, which is a good size subnet. It's big. You want to try to avoid having just enough host bits. I mean, sometimes it's unavoidable in the problems we do, but in real life, you want to avoid where, I've got 62 hosts, so I'm going to subnet and give that subnet 6 host bits. Well, what if you add a computer? You're screwed, right? You're done. I mean, if all of your addresses are already used, and actually, furthermore, you got to think about not just the number of computers. So when we say host, we're including everything that needs an address. But in real life, you might translate that to, okay, I've got this new wing of our office and there's 14 computers. Okay, we need 4 bits for that. And if you subnet to give 4 bits, okay, 2 to the 4th is 16, minus 2 is 14. That takes care of your computers, but there's a router interface, your default gateway that needs an address. There's probably, if you're managing a switch, printers need IP addresses. So, don't get locked into how many computers are there in this network. You got to think about the other devices that need IP addresses, like printers, the router, of course, any managed devices like switches. But when we say hosts, we mean that all the devices are counted for. All right, so, so let's do that, problem. Let's see, if do they do it on the next page? No. Oh, jeez. All right, so we have, did they give us an actual address? No, it just said. Oh, wait a second, I'm on the wrong screen here. There we go, 172.16, okay. So for those that weren't quite sure how we arrived at what was arrived at. Okay, so this is what the original network and prefix was, and we need 100 subnets. And again, there's a couple different ways to go about subnetting problems. You can say, how many subnets do we need? Or how many hosts per subnet do we need, and approach it from either direction. We're going to do it from the number of subnets in this problem. So if we need 100 subnets, then we basically just look at our table and say, what power of 2 gives us 100 subnets without going, so the 7, 2 to the n, so the n is the number of bits that we have to reallocate, right? So that means we need 7 bits. Is 2, 7.
So how do we know we need?
Because the word says that
Because
squared or whatever, 2 to 7.
we need 100 subnets, then we just look at the table and say, what power of 2 gets us as close to 100 as possible, because it's always going to be a, a power of 2 value. Which power of 2, how many bits will give us that 100, or as close to it as possible? And that's going to be 2 to the 7th.
Do you have a printout of that table somewhere, or we can just copy it?
I would just write it down as many times as you need to get it ingrained into your head.
That's a lot.
So, yeah, so 7 bits is what we need. So that means that our so we should know that this /16 looks like 255.255.0.0. And now, after we've decided how many bits we need, we're gonna rewrite our network ID, and our new prefix is 23, because the 7 bits added to this original 16 gives us 23. So what does that subnet mask look like?
255, 255.
Okay, so what do we do? 1, 2, 3, 4, 5, 6, 7 bits.
Oh, that's
So 254.
The last octet will be 0. So all we have to do is take that 7 bits that we've reallocated. Okay, that 7 bits that we reallocated, put them down into the new subnet mask, put them down in binary if you need to, is what I did. And then put those numbers into our binary to decimal conversion table. If you were to put binary 1s in each of the binary to decimal conversion tables, you'd get 254. So 1111110 in decimal is 254. So that's our new subnet mask, 255.255.255.4.0. So that means we have the entire fourth octet for host plus one additional bit. So that's one thing that starts to get confusing is when your host field occupies an entire octet plus a couple bits, 1 or 2 bits or more in the adjacent octet. But we'll worry about, enumerating the subnets a little bit later. We'll just say that for these purposes, this is, the end of the problem. We got the new prefix and the new subnet mask. Okay.
Okay, forgive me, but I missed one thing here. Why is it /23? Shouldn't that be /25?
Why 25? Where do you get?
Because the cider shorthand,
No. Okay, so,
There's 7 bits.
yeah,
So you add 7 to the 16.
the,
oh, you're adding it. Okay, never mind. She just told me.
so that, the cider shorthand, we'll see what, that comes into play when we start off with the 255.255.255 subnet mask.
Okay.
Okay, so this /25 through /32, which you'll never use.
Right, so she was.
Those are only applicable when you're going from /24 to /something higher.
Okay,
If you needed like 130 subnets, would you be able to just go to the next octet, right? It'd be like all ones, and then you'd start at the last octet.
You needed 130.
Because it would be higher than 128, so it'd be like.
Well,
nine
right. You would
bits.
just extend this.
because it
You
started.
would basically just say how many more
You'd
bits.
use that last octet to do that, right? The 0?
No, actually,
No?
you'd still be using the third octet, and I'll show you why. If you needed 130, like you said.
Yeah.
Well, 7 bits doesn't cut it, so we need 8 bits. And so it would now look like 255.255.255. So it would go from /16 to /24.
I get it.
If you needed 500 subnets, then we would go into the fourth octet.
Okay, that's, okay.
We go to /25, which would be 255.255.255.128.
Makes sense.
Yeah, so yeah, if you go past 24, then you gotta start working on that last octet. Okay, so let's stop here and take a break, and then we'll finish a few of the slides and just do some problems related to what the slides are telling us. Because that's usually the first step in the first 2 steps in doing a subnetting problem is how many bits do I need to reallocate for the number of subnets required? That will tell you what the new prefix is. You just add that number to the current prefix. And then what does that new subnet mask look like? Once you've got that, then you can start doing the rest of the steps, which is enumerating, what are my subnets? What are the addresses that I actually have created by doing that subnetting? So we'll do some problems with that when we come back. So give you a good number of minutes. So 1/4 gives you about 12, 13 minutes. And I'm gonna try to fix this whiteboard thing.
Hey there, how you been?
Is this same as that, but written differently?
Yeah, it's the same as this. The only thing that what you did is you have
Group number.
you have the subnet mask value for the bit positions. Like, so if just the first bit was part of the subnet mask, then it would be 128. If the first 2 bits were part of the subnet mask, it's 192. Whereas this table is giving you the power of 2 at the top So the 2 to the 0, 2 to the 1, 2 squared, etc. And then the row underneath it is just what that power of 2 translates to. So 2 to the 0 is 1, 1 is 2, and the 7 is 128. So that's one that you don't have that in here.
I should write it up.
To me, I'm not sure.
This was from the video from the announcement. The resources.
Oh, so that was one of the videos gave you this?
Yeah.
Okay, yeah, I actually don't know what's in there. I mean, I know that some students have told me about those websites and they said that they, that they used them. I didn't actually. Need to, so.
Right.
But, so, yeah, I mean, there's nothing wrong with this information. It's just that I think well, what I would add to this is the top is the power to the 0 to the. So that way you can easily look at, how many subnets do we need? 64. How many bits is that? 6. Right? So if I need 64 subnets, I need 6 bits. So this row is the power of 2 value. So I would put the top 2 to the 7th, 2 to the
Right,
6th,
okay.
2 to the 5th, all the way to 2 to the 0.
Okay, and block size is group size, right? The same.
Yeah.
Okay,
Mhm.
all right, thank you.
Yeah.
Carry on.
We can take a photo. Are you, when will the recording of class be posted?
This recording?
Yeah.
Most likely we'll go until at least 8, which means it'll be a long recording, which means probably not till tomorrow. Because it takes a long time to process.
Yeah.
Locally, then I gotta download it, which doesn't take too long, but then I gotta upload it to YouTube and it takes YouTube a long time to process. So, yeah, it takes me I also trim it so that the initial 7-8 minutes of us just,
Yeah.
shooting the breeze isn't in it. So all that takes me an hour and a half to do. So it'll
No, I was
be,
just curious. just to-
it'll be tomorrow.
Sure. All right. Perfect. All right. Thank you. You have a good night.
You too. Okay, so how do I change this? All right, okay. Davis came. Skeeter, you came in?
Yeah.
Late? Yeah, okay. That was it. Cool. Start using text. All right, I think get going. Okay, I guess most everybody's here. A couple of people had to leave. So subnetting to meet the requirements. So like I said, there's there's at least two ways to go about it. And usually when you're learning subnetting and you're given a problem, you'll be told, subnet to accommodate this number of subnets without regard to the number of hosts per subnet. Or you'll be say subnet to accommodate this number of hosts per subnet. And really, the easiest way to go about that, if that's all the problem is, and you're not asked to, do anything besides coming up with like a new prefix and subnet mask, you basically just need to say, how many bits do I need? Okay.
Right.
If you're subnetting for the number of subnets, how many additional bits do I add to the subnet mask? And so if you start off with /16 and you need 8 subnets, then you add 3 bits to the subnet mask. And now you've got a /19 or 255, 255, 224, .0 subnet mask. If on the other hand, you're told, okay, you start off with a /16 subnet to make sure that you accommodate 30 hosts per subnet. Well, if you're doing it that way, you just have to say, well, how many bits do I need for 30 hosts? I need 5.
No.
I need 5 bits for 30 hosts. So you create your subnet mask by simply filling in the host bits that you need, in this case, 5. So you'd put 5 zeros in the fourth octet, and all the other bits, all the other subnet mask bits are binary 1. And that's all there is to it. So let's look at what problems they have. So number of host addresses or number of individual subnets need. sometimes in real life, you probably need to consider both. You probably need to say, well, I need X number of subnets, and at least one of my subnets has to be, accommodate 100 hosts. But the others only need to accommodate 30 to 50. And so that's where the problem is like not as straightforward, because you may run out of addresses if you make all of your subnets able to accommodate 100 hosts. And so you're going to need a different subnet mask for the 100 host network compared to the one that only needs 30 or 60 hosts. And that's where variable length subnet masking comes in. But for the more straightforward problems where everything's going to be the same subnet mask, you just have to say, all right, how many bits do I need for 2 subnets? I need 1 bit. How many bits do I need for 16 subnets? I need an extra 4 bits, going from a /24 to a /28. And you don't worry about the hosts if that's what the problem is. And then going the other way, if they say you need to accommodate, 62 hosts per subnet, that means you need 6 host bits, 6 0 bits, and the rest are going to be binary ones in your subnet mask. All right, so let's see if this gives a problem or whether I need to.
Can I ask a question?
Yeah.
In the lab, one of the questions is, it says, configure the interface with the last host address at 192.168.10.0/24. How do you get to the last host address?
Say that again?
The lab, it says, configure the router interface with the last host address, and it gives you the 192.168.10.0/24. How do you get to last host address?
You can answer that question. If you have an IP address or a network ID, or I'll write it down.
Because I know we did it in the last class, I just don't remember.
So I'm actually gonna go ahead and. So if you have 192.168.10.0 and .10.0 geez, /24. Okay, what is the last host address of that network? 254. Right, because it's a /24, so the entire 4th octet is the host field. And what are the host addresses in a /24? When you have the entire 4th octet to use, what are the possible host addresses? What's the first host address? 1. And what's the last one?
255.
254. 255 would be the broadcast, right? So the last host address is 254. The second to last, and a lot of people got this wrong on the skills exam.
All right.
You use the same address for your default gateway as you did for your host.
So the second to last is.
So the second to last is 253.
Come on, is that right?
So that's all. You just need to figure out, what am I looking at? I'm looking at a /24, which means the entire 4th octet is host.
And the network is that, the 0.
The network ID is 10.0. So the first
So
first
what
host
was the-
address is always add 1 to the network ID.
Okay.
And I say add 1 because you're going to get network IDs like 192.168.10.16.
Right.
So the first host address in that subnet would be 10.17.
Huh.
So that's why I don't say it's always going to be .1, because if your network ID is something other than 0 in the 4th octet, then you add 1. You just turn the
Oh, it's
one,
always
the
one and
rightmost bit on. That's another way to look at it. No matter what your network ID is, no matter what it is, your first host is always just turn that rightmost bit on to 1. That'll be your first host. Your last host will be all the host bits except the last one being on.
Thank you.
Okay, yeah, okay. This is given a problem, but the graphic is so small and the numbers are so small that I'm just gonna use my own. So the next slide gets right into VLSM, but I don't think we want to go there just yet. So the thing to do is let's do some just some ordinary subnetting problems. I'll do a subnetting problem where we're working in the 4th octet. That seems to be the most common that you know, the beginning problems. So let's say our address is that. And we need 16 subnets. So that's how we're going to approach this problem, is the number of subnets needed. So we basically have to reallocate the appropriate number of bits from the host field, which is the 4th octet, and make enough of those bits, network bits, to accommodate those 16 subnets.
So it's 4, and then you add the 4 to the 24 to the 28.
The do something with my whiteboard. I'm gonna get my table up here. Okay, so we need 16 subnets. So what power of 2 gives us 16? All right, so 4. That means that we are going to add 4 bits to our 24 prefix and subnet mask. So let's first say, what is the subnet mask for this guy? /24 is 192.168. Gosh, jeez. 255.255.255.0 is your /24. With 16 subnets, we need 4 bits. Okay, so that's gonna give us a new subnet mask, or first off, it's gonna give us a new prefix, 192.168.20.0/what? 28. So we just add the number of bits that we need to create that 16 subnets to our original prefix. And what is the subnet mask that gives us? Got what?
240.
240. And how do we get 240?
We get 22.
So we get 240 by
28, 64, 32.
doing, we put our 4 bits, this is a 4th octet, put our 4 bits down into our field, into our table. So this is what the 4th octet looks like in binary. So we know that 255, 255, 255, that 240 is because we took 4 bits from the host, but it made them network bits by making them 1 bits in the subnet mask, 1, 1, 1, 1. And then here's our remaining host bits, the 4 zeros. Okay, so host and subnet. Subnet bits. All right, so so that's where the 240 comes from, and that's where the 28 comes from, just adding the 4 bits. So if this was the end of the problem, if all you need to do is come up with a new prefix or a new subnet mask, you're done. But a lot of problems are going to ask you, okay, do that, but also what is the network ID for the 3rd subnet?
So, okay.
Okay, so what is the network ID for the 3rd subnet? Well, in all cases, the first network ID is always the original network ID.
Oh.
So the first one is always going to be 192.168.
Huh.
In this case, 20.0. Okay, with the new prefix. So that's the first one. What's the second network ID going to be?
Is it gonna be 16?
Dot 16.
Dot 16, exactly.
Then you add 16,
So-
16, 16 like that.
And so how did you get that 16?
Cause it's the 2 that are 4,
That's
right?
how many subnets there are. I mean,
That
Cause it's 2
actually
that are 4, is your 16.
isn't it.
So the 3rd one would
Um,
be 2 to the.
Because if it was
32,
0,
16, 32.
you're creating 32 subnets, then your first one would be .8. So the number of subnets in the first non-zero subnet aren't going to be the same. They just happen to be in this instance, so coincidentally.
it's the number of
But
bits then.
you basically, you look at the rightmost bit of the subnet mask, okay? The rightmost bit of the subnet mask. This guy right here. That's the 16's place. That is your increment for your subnet values. That will always be your increment. So once you've got your bits down in your table, you just look at that rightmost bit and say, that's what my subnets are going to be incremented by 16.
So the next one would be 32.
The next one would be 32. Yeah. And the next one. As long as you can add 16, oops. This does, oh, I gotta select it. So weird, it's not letting me, oh, there we go. Okay, so, and so on, 64, 80, 96, 112, 128, 144, 160, 176, 192. I'm gonna go all 16, 208, 224, 240. And I know that I'm done when the last subnet that I put down is gonna be the same as the last octet, or the last non-zero octet of the subnet mask. So 240 is the last one.
Huh.
And of course, the other way to look at it is, if I kept going, what's my next number after 240? 256, which isn't a valid, it's not a valid value for an octet. So, and we're working in just the 4th octet. When you're working in multiple octets, then you can, cross over into the next octet. But here we're sticking in just the 4th octet. So once we get to a number where the next subnet would be more than 255, then, we're done. So that's how you enumerate your subnets is once you get the subnet mask, your first subnet is always the same as your original network ID with the different prefix. And then all the subsequent ones are just increments of the rightmost bit field of, when you put those bits in the table. Another way to look at the increments would be how many hosts per subnets do I have? Okay, this is the host field. I gotta forget that I've got. So here's the host field. Right, so how many hosts per subnet do I have? Okay, well, there's 4 bits, so 2 to the 4th is 16, but we have to subtract 2.
That's right.
Network ID and the
That's right.
broadcast.
It's 2n minus 2, right?
So we have 14. But so if you have 14, if you have 4 host bits, which means there's a total of 16 addresses if you include the network and broadcast, then that means, of course, that the next subnet has to be 16 more than the previous. Because once if there's 16 host addresses, or 16 addresses, I should say, but total of 16 addresses with 4 bits, only you just have to exclude 2 for when you're assigning to hosts, but there's a total of 16 addresses there. So obviously, once you use 16 addresses, including the network ID and the broadcast, then the next subnet has to be that number, 16. And then once you've used all the addresses in the 16 subnet, the next subnet has to be the next increment of 16, 32. But I prefer to look at it as just look at that rightmost bit in the subnet mask, and that's your increment. Okay, so that's then the next thing to know is, well, what are our possible host addresses in? What are some of our host address? Whoops. Make that one. So what are our possible host addresses here? What's the first possible host address in this one?
So it's
In the 20.0 subnet, what's our first? Dot one. It's always just turn on the rightmost bit, and which will be the 1 bit always. All right, so that's our first. And what's our last host address?
15.
Okay, that's going to be the broadcast.
14.
But the last host address will be 14.
14, right.
But we do need to know the broadcast. So the broadcast, just say, put it up here. It's gonna be 2.
Right. Oh, okay. Yeah.
So that's the broadcast for the .0 subnet.
Right.
Now, what about the .16 subnet? What's the first host address?
17.
Right, just add 1 basically.
Oh, yeah. Excuse me.
Right.
Because
And the
16
last,
access the network address, right?
yeah, 16 is the network ID. So 17 is the first host address, and the last host address,
31,
31 would be the broadcast, so.
30.
So the way to look at it is look at your next subnet. your next subnet here is 32, whoops, is 32. So to get the last host of the previous subnet, just subtract 2. To get the broadcast for the
Broadcast has
previous
to be one less.
is just 1 less, right? Yep. And if you look, it follows that pattern we saw before. 17 is 1, 1, 1. I'm sorry. It's not. 17 is in the entire octet, 0, 0, 0. That's the 16, that's the network ID part. And then
0, 0, 0,
0,
1.
0, 0. So in that one slide, the pattern said that the first host address will always be all the host bits being 0 except the last one. 1. And then the last host address, 30, is going to be 0. That's your 16 for your network ID. And then 1, 1, 0. So 16 plus 8 is 24, plus 4 is 28, plus 2 is 30. So that gets you your 30. So the last host address, the host field is all binary 1s except for the last, which is a 0. And then, of course, the broadcast is, again, the network ID. Sorry. Followed by all host bits being. So 16, and then you add 24, 28, 30, 24, 28, 30, 31. So that's the broadcast of 30.31 for the 16 subnet. And the 32 subnet, it's just going to be 33 is the first, 46 is the last, 47 is the broadcast. And then for the 48 subnet, the first host address is 48 subnet. The first host address is
49.
49, and the last host address is
What does that go to?
this next one would have been
16,
64.
60, 64, I think 60. 3 is the broadcast.
63 is the broadcast, 62 is the last host address. So 49 through 62, 63 broadcast. Okay, so that's, yeah, that's, one of the types of problems that you need to be able to solve is when the problem says, here's your original address, 192.168.20.0/24, for example. You need 16 subnets. What's your new subnet mask? So you just take your original subnet mask, add the number of bits that you need, in this case 4, put those 4 bits in your table, do the binary to decimal, you get 240. So that's the last octet of your subnet mask. And then you need to be able to enumerate the subnets, because you'll be asked, like, what's the last host address of the third subnet? So in that case, it would be 192.168.20.46 would be the last host address of the third subnet.
So if I'm looking at the chart, my brain is working.
Mhm.
If we needed 32 subnets, then we would need 5 bits.
Yes.
Okay.
It's working.
All right, let's do another one. Like,
A couple of charts up, where the number,
delete the whole
for
thing.
the 28 CDR, number of subnets says 4,096. Is that the number of total addresses that will be available if you were to count them in that subnet?
In which subnet?
The we just did 20 slash 28. Couple of charts up. On the
Slash 28 means that the network ID is 28 bits and there'll be four host bits. So you only have 14 hosts per subnet.
The chart I'm looking at where
We're
it
looking at the
says,
slides on the PowerPoint, is that what you're talking about?
yeah, your PowerPoint and a couple slides up is I'm trying to connect the dots of where the 4096.
Okay, 4,000, that's a lot of, let's see, that's gonna be like 12 bits or something.
It's on the create subnets with the /16 or a /20, it says 4,094.
This all at once, huh?
And if we were to add up all the addresses between all the number of subnets.
Okay, so which one are we talking about?
What's the table thing? What slide?
It's above, it's before that couple. Right there.
Okay. So, okay, so what this is saying is if your original, it was /16, okay, in the problem I just did, the original subnet mask was a /24, 255.255.255. In this table, they're saying, assuming that your original network ID is a /16, then if you went and subnetted and added 12 bits, went from a 16 to a /28, 2 to the 12th would give you 4,096 subnet. So it depends on where you start from.
Right.
Yeah, the slash number by itself can't tell you how many subnets you're going to create just by itself. You have to know what was your original prefix value. If your original, like your original prefix value could be /26, right? And if it's now, and you subnet to a /28, you have 4 subnets. That's all you've got, because you went from 26 to 28, just 2 bits difference. So you have to know your starting point to know what the slash value translates to in terms of number of subnets. Now, the slash value will always tell you how many hosts, because the slash value always tells you how many bits are left, right? So no matter what your starting point was, if you subnetted and you're now at /28, well, there's only 4 bits left in a 32-bit IP address. So it's always going to be 14. If you started, again, it doesn't matter where you started. If you're /23, that gives you 9 bits of host, you'll always have 510. So the slash value always determines the number of hosts, because you just subtract the slash value from 32, and that gives you the number of bits. So 2 to the n, whatever bits that is, minus the 2, will give you the number of hosts. But it can only tell you the number of subnets based on the starting point. If you don't know the starting point, you can't do the problem.
Yeah.
So if they just say, here, you have a /28, unless they say, assume, you know, that the starting point was a classful subnet mask, then you can do the problem, but otherwise you can't. You always have to know what your starting prefix is. Okay, so let's do another one. Let's do another one in the where we're working in the 4th octet, just so that we're clear on doing those types. So let's say and I'm just gonna do this because I want you to understand that since I'm gonna give you the initial prefix, it doesn't matter what class address this is. I'm gonna tell you what your initial prefix is, so just throw out the idea of class here. So that's your initial IP address / prefix. And the problem is we want to have I'll just make it a nice round number, 8 subnets. Okay, so what you need to do is come up with new prefix, new subnet mask. That's what initially, that's what you need to do, and then we'll do the rest. So just so everyone's clear, the original subnet mask is what?
255, 255.
Okay. So again, that's a class B, but it doesn't matter because I'm telling you that that's your original prefix. That's what the ISP gave you. And so that's what you have to work with. You only have the 4th octet to do your subnetting. So take a few minutes, come up with a new prefix and a new subnet mask. And I also want
last octet would be 240 and the prefix would be 28. I mean, exactly what it'd be week 2 to the 3rd power, but we want a little more, right?
3 to 24.
No.
So are we following that rule? We're not
No.
gonna go for exactly.
No, the rule we're following is we want
Oh,
exactly
exactly eight.
that. Yeah.
Then
No, let's
224
just
and
just give people a little bit of time before we start putting numbers down. We'll say, I'll go at 5 till by that clock. That gives you about 2-3 minutes to come up with those 3 things: new prefix, new subnet mask, and hosts per number of hosts per subnet.
Oh, host.
Right, yeah, it's,
2 to the 3 minus 2. So. And minus 2. Oh, 6 still.
16. I'm gonna ask one of you guys in Zoom for an answer in a few minutes, since I keep forgetting about you. So. There might be a girl in there too, so I shouldn't just say guys. No, I guess there isn't. It's just guys today.
Did you see the cheat sheet? Download. It'll say Cisco Convenience Team.
Okay, another few seconds. So. Okay. Anthony, did you get a answer for the first part of the problem, a new prefix? Is your mic?
The-
working? Yeah,
/27.
go ahead.
At first I thought 29, but I'm second guessing myself.
Okay, what did you second guess yourself to? So
27.
yourself was a good idea. So what did you?
27.
27, okay.
Yeah.
All right, so that's correct. So you got that by what? We needed 8 subnets, so we have to look in our table and we see what power of 2 gives us 8. Right there. So that 3 in the 2 to the cubed is the key. So we need 3 bits. So we just add that 3 to the 24 to get our 27. So we basically have extended our subnet mask from 24 bits, added 3, it's now 27 bits long.
Mhm.
So now, does anybody else in Zoom, Johnny or Devin or Andrew or Jerry, have the new subnet mask? Jerry,
Yeah, 255, 255, 255, 224.
You have to have ones in order.
good. So that comes from that 255, 255, 255, 224
Oh.
comes from,
That might be wrong.
there's 3 bits.
Okay, oh,
We
that's.
put them in our table, always starting from the left. And then the rest of the bits are 0 for our host bits. And so you just add up those 3 columns where our 3 bits are, 128, 192, plus 32 is 224. That's our new subnet mask. Hosts per subnet. Anybody in Zoom get that? If you
Is that
look
8?
at, go ahead. Sorry, go ahead, Jared. Or Anthony, whoever spoke up.
32.
32, okay. It's 2 to the 5th. There's 5 host bits. But remember, Jerry, you have to subtract 2 always. So 2 to the 5th is 32, so that part is correct. But we have to, for the number of hosts, which means where we could actually assign an address, we need to subtract the network ID and the broadcast. So that gives us 30.
I thought it would be the zeros. Aren't the zeros the hosts? So
Yeah.
it'd be 16.
No, because there's 5 host bits, so it's 2 to the 5th. Don't look,
Oh.
you don't look at that number, you just count how many zeros there are.
Okay.
There's 5 zeros. Just like there's 3 ones for the subnet part, that gives you 2 cubed is 8 subnets. So however many zeros, 2 to the n, in this case 5, 32, then subtract the 2 for the broadcast and the network.
So I got a little mixed up, so I got like 248 somehow, it's like I was adding
So there's 5
7
host
to the
bits.
3rd power.
So there's 5 host bits, right? 5 zeros.
So you got 248 for the 4th octet of the subnet mask?
2 to the 5th power.
Yeah, for like the cider 27, like
Subtract 2 to get 30.
See what the new subnet.
How does /27 get you 248?
So I understand that's not the correct answer. I was
Okay.
just like, I guess I'm missing a step. 'Cause
So if the /27, you just look at where do you put those binary ones in our table? And then you just add up those columns. So the 128 plus the 64 plus the 32 is 224. Okay,
How do we get those 3 bits? Is that from getting to the 2 to the?
2 to the 8. or
8
2 to the
subnets.
3rd Get you to 8 bits.
8 subnets, we need 3 bits,
Yeah.
right? Because 2, so basically the subscript or the superscript above the two, which is above the column of the value that power of two makes, that's the number of bits that you need to reallocate to the network. So since 8 is the number of subnets we need, we take the power of 2, which is 3.
So if it was 4.
3 bits, 1, 1, 1. That's what you just put however many bits it is in your table, and
So what if it was like 27 segments in between 2 and 52?
then you would take the closest number, which in this case would be 32, so you'd need 5 bits.
Okay.
Yeah, you always go just to the next value. So if it was 27, 16 is not enough, so you got to go to 32. If it was 33, you'd have to go to 64. Yeah, you're so damn close, but it's not going to work. That 64 or 60 or 33rd subnet couldn't be made if you only had 5 bits. Yeah.
To find the number of hosts, can you just do 256 divided by the subnet and then subtract that answer by 2?
256 divided by the subnet.
Yeah, the amount of subnets.
Yeah.
Then you
Wait a minute.
And then you subtract that answer by 2.
So the number of hosts.
Which, yeah, be 30, yeah,
2
256 divided by 8 minus 2. Yes, you could do that as well.
So would the next address be 60, we'll go by 30? So 172.44.28.30, that would be the first address, right?
Well, no, always look at the rightmost column.
That makes
The
sense.
right, this is the 3 bits. That's the 224, right? The 111.
So it'll go by 32.
So,
but
yeah.
usable, the 30 is what's usable.
Well, that's what's usable in each subnet, but when you're looking at finding the next subnet, you've got to count the broadcast and the network ID. So you got to go by the 32. Yeah. So however many hosts per subnet, it's 30 because there's 5 bits and 2 to the 5th is 32, but we subtracted 2. So our increment is going to be though the 32 because each subnet has to account for this network ID and the
So the
broadcast.
first address would have been,
Well, the first address of the first subnet is going to be .1. The first well, let's put those down. That's probably a good idea. So our first subnet is going to be always the original.
Plus 30.
And then our next one,
20 times 27.
we just, okay, so again, 2 ways to do it. Look at the rightmost bit of your subnet mask, because this is this 111 corresponds to that 224. So the rightmost 1 bit is pointing in the 32 column. So that's our increment. Or you say, how many host bits do we have? We have 5 host bits, 2 to the 5th is 32. That's our increment. The same result. Either way you do it. You can either say how many host bits, 2 to the n, and that's our increment, or just look at that rightmost.
so that address would be that 32.
About 32, yes.
And each one of those is that is what is the subnet?
Isn't that supposed to be 27?
I'm sorry. It is 27. Yeah. It does, for some reason, it doesn't let me edit, or does it? Let me edit that. Oh, yeah. No? Yeah. Sorry about, I was stuck on the last problem. 27 is correct.
It's okay. I was like, wait.
Yeah, remind or correct me when I do that, because it's sometimes hard to think and talk at the same time. So
Just make them up.
select. Okay. Okay, so and then the next the next subnet ID is gonna be what?
64.
Yeah.
And 96.
And then 96, and then 128, all the way up to 224.
And those are each different subnets, the 32, 64.
Those are all subnets. Those are all the network IDs for those networks. So that means that you also have to figure out the host. So if you needed to find out, what's the first host address? Well, for the first subnet, it's always easy because it's always just gonna be .1. If you're starting with, a .0 network. So 28.1, and then the last,
Could be 31.
could be what?
31.
Thir-
Or no, 30.
30. Always
Right,
subtract
30,
2
that's right.
for the
I was gonna
host,
take off the-
1 for the
take off the
broadcast. So 1 through 30, that's gives us 30 addresses. That's the other way. Check your work. If you put 30 down for the number of hosts, and assuming you were correct with that, then when you put the range, you better not have more than 30 addresses in that host range. And then the next address is the 31 is going to be, I'm just going to put .31 is the broadcast.
These are all of the 28.0 network, right?
28, yep, all in
That's the
28.0 network. And now for the .32 network, our first address is
33.
33, just add 1. And then our last address,
62.
62. And our broadcast is
63.
63. And 65 through 94, and 95 is the broadcast, 97 through 126, and 127 is the broadcast.
So would that be like all the addresses from 0 to 32 would be like one department, and then all the addresses from 33 to 60 or another department?
Yeah, they would all, each of these, every subnet in a network has to have a router interface associated with it, because that's the only way that the hosts in the 28.0 network can talk to hosts in the 28.32 network is this through a router. So each subnet has to have a router interface. Now, that sounds like a lot of interface, like you've got a router with, 8 interfaces in this problem, 16 interfaces in the previous problem, right? Well, that's not in reality how it usually goes, because routers like Cisco routers and layer 3 switches have what's called virtual interfaces. So a single physical port can actually be assigned multiple subnet IDs. You'll actually see that when we get into configuring routers, what's called router on a stick. And that'll be, I think, the next class in 150. So you don't, you need a router interface per subnet, but they don't have to be physical interfaces. If your router supports what's called sub interfaces, then you can assign multiple subnets to a single physical interface. Okay, so that's a couple of problems, or they're pretty typical of subnetting a /24, where you're basically starting with a 255, 255, 255, 0. It's not really any different if you're starting with like a /16. Whoops, that's not what I wanted to do. Okay, so I think I'll do one more problem, and obviously we're going to be going into Wednesday for the lecture part of this. If we don't get lab done this Wednesday, then we just push it to next week, because this is important, and it's the hardest subject that you're gonna run across, at least until we start dealing with probably CNT160, which most of you aren't taking. So this is probably the hardest topic for most of you. Some of you may have it, which is good, or starting to get it. So I don't want to, short shrift it, because if you were to try to take a Cisco certification test and not know subnetting, you might pass, but you'd have to probably get everything else right, which I'll tell you is pretty hard to do. Those tests are not easy. They get harder as time goes on. So, if you can get most of the subnetting questions right, if you end up taking a CCNA test, then you can miss a bunch of the more complicated, routing and switching questions. So it's a good, gives you a little security blanket. All right, so let's look at doing a subnetting a /16. So I'm just gonna put in comma. Okay, so I'm gonna basically ask the same questions for this one, and just to see if you are thinking right when it's starting from a /16. It's really no different, except you're not going to be working in the 4th octet. You'll be working in the 3rd octet. So I want the new I'll tell you how many subnets. I'm going to do the same exact problem. So, gosh darn, I hate this annotation stuff. New prefix, subnet mask, and number hosts per subnet. Okay, so work on that for just a few minutes. It's kind of like the last problem, except shifted over 1 octet to the left. One thing I'll tell you is that the number of hosts per subnet is going to be much, much bigger. Okay, does anybody have a new prefix?
19? That's as far as I got, like,
But 19 is correct. Okay, so that's a new prefix. Let's put the original subnet mask down so that we have. And so the new subnet mask that goes with this /19. So again, we take the 3 bits and we put them into our table. Now, the difference between the last problem and this problem is this is the 3rd octet that we're doing this in, because our original subnet mask was 255.255. So those 3 bits that are being added to the network ID go here in that octet. And the 4th octet is just left alone, it's all host. So the 3rd octet looks like this, 111 followed by 5 zeros. So the new subnet mask is what?
224.
224 again. Yep. But we got a .0 at the end, right? Because we're working the 3rd octet because we started with our network ID was just the first 2 octets. So any subnetting up to 256 subnets is, you know, if we need more than 256 subnets, then we'd be working in the 3rd and 4th octet. But up to 256 subnets, we are working in that 3rd octet with our new subnet mask only. And then the 4th octet is left alone as host still. So that means we've got in our 3rd octet, 3 network ID bits and 5 host bits. But we have the entire 4th octet for additional host bits. So what does that mean in terms of the number of hosts per subnet? First off, give me the power of 2 for the number of hosts per subnet instead of the actual decimal number. 13, 2 to the 13th, right? Because 5 host bits in the 3rd octet. So this is the 3rd, whoops. 3rd octet. And so we've got 5 host bits. And then the 4th octet is here. And there's 8 host bits. 8 zeros there. So that's 13 zeros. So 2 to the 13th, or I think that's 8,192.
Yeah.
So 8,190 hosts. If we 8,190 hosts. That's a lot, which, you know, isn't very practical, but you know, not all the problems are practical per se. They're just making you do the mental gymnastics so that you understand subnetting. Well, in some cases, it might be practical because you may have like an ISP that's got a huge bank of IP address space. You know, they might give out, you know, a /28 to somebody, a /24 to somebody, a bigger company. And, you know, what they might have left over after a /16 is, you know, a /9 or /19. Now they may not use, you know, somebody may not create a subnet with 8,190 hosts. What's more likely is that ISP that has a /19 left over after they already reallocated some stuff will subnet that again. So the subnet, the /19 into like a /26 or whatever they need for their customers. So that's why you have to, you know, say, what's my starting point? Your starting point could be anywhere from a /8 to a let's say 29, even though that would be unlikely, but let's say a /8 to a /26 or 27 might be your starting point. And then you may have to subnet that some more. We're starting on octet boundaries because, you know, when you're dealing with like internal networks, private networks, that's usually what you're doing is starting with a /16 or /24 or something like that, and then subnetting that more. But if you might get from an ISP, you know, you might get a /26 and you've got 6 bits to work with in the host. You may actually want to subnet that again to provide, you know, a bunch of public IP addresses in one location. So like a /27 in giving 2 to the 5th or 30 hosts in one of your locations and a /27 in another location. So you might divide up a /26 that an ISP gives you into 2 /27s. So again, you got to know where your starting point is, and it may not always be on an octet boundary. Yeah.
Okay, so IPv6 makes all this crap obsolete, right? And are they still making devices that don't have IPv6? Like with the amount of time it takes to make a device obsolete now, like why are we still doing this?
Because IPv4 still rules the world.
Why?
Because it costs money to replace all the equipment.
Well, it costs money to redesign. Yeah, replacing some equipment that doesn't support V6 is one possibility. Like these switches, only half of these switches support IPv6.
Right, but they don't make those anymore, right?
They probably don't make them anymore,
Like hubs,
but there's companies that have 30, 20-year-old equipment that still works great for their purposes.
They need to get their shit together. That's hard.
Why don't you write them a check for $100,000 to redo their network?
Send them a strongly worded email.
Mom and pop shops can't handle that kind of.
Yeah, even big company, actually big companies, it might even be harder. It's like, if it works, yeah, to redo everything to IPv6, we're gonna have to spend $3 million or $10 million if you're really big. Well, we'd rather spend that on a marketing campaign. If it works, if what we have is working. Now, eventually, presumably, I've been saying this for 15, 20 years, eventually we're gonna be forced to go to IPv6.
Well,
I don't see it like, I don't see the end of the tunnel there yet, where it's like, okay, within 2 years, we better be there. I bet, I will not be at all surprised if 5 years goes by and we're still entrenched in IPv4.
But like the way engineered obsolescence goes in electronics, like iPhone, 7 is obsolete now and isn't supported? Like,
still works though, right?
I mean, I guess it's not supported anymore.
Well, not by Apple, right? But I mean, most of the stuff I have isn't supported anymore. I mean,
So it's a big security issue.
Well, yeah. I mean, if they're not making updates for the iOS version that runs on that Apple, on that phone, then you're stuck with whatever vulnerabilities that are in it.
Right.
And if someone finds new, but the thing is the hackers, the people are gonna spend the time to go and hack a iPhone 7. They're gonna be like, what's the risk reward? How many iPhone 7s are there still out there? Phones are a lot different than infrastructure equipment.
Right.
People change them
That
every
makes
year in some cases. I don't know where they get the money to do that, but or the patience, because you gotta, redo your everything on your phone.
Well, that
at least
part's
I
getting
do.
easier.
Yeah, that's true. But still, I mean, infrastructure equipment is, you know, much more, it stays, people are still using Windows Server 2008. I mean, that's 15 years.
Right, my brain wasn't thinking big enough.
They may actually be on different equipment now, but they left the operating system because it's like too much of a hassle to go and test all of our apps, and some of them may not even work because they're using apps that, you know, were 32-bit apps that would work on Server 2008, 32-bit edition, but may not work, and they don't want to find out if it doesn't work. You know, especially smaller to medium-sized businesses that don't have, you know, 50 IT guys to do all that stuff. Eventually, you know, companies have to be, you know, what happens to companies, their hardware goes kaput and they're forced. And then they're like, go through a couple months of pain and suffering, but you know, now they're upgraded. That's what usually happens because they don't prepare for, you know, especially like smaller end businesses. In any case, I mean, by college, I asked Stephanie, the network administrator, a couple months ago, said, can you give me a prefix, a 2000, you know, a IPv6 globally unique ID prefix, so I can, you know, start using IPv6. We don't have one yet. So we don't even have an IPv6 global ID from our ISP yet by college. And we're not exactly like, you know, really in the boom, you know, in the caveman times of tech. We keep up pretty good with most stuff, but the question becomes why? Why? What's the compelling reason to move to IPv6 other than to avoid subnetting? And hopefully the network admin knows how to subnet, so she doesn't care. I know she knows how to subnet because she was in my classes. So, but yeah, it's like that's what it's gonna take. It's gonna take the killer app that sort of like, you know, people didn't bother going to high definition television until it was actually channels, right? The televisions were there first. And, you know, the people with tons of money bought them, even though they could only, you know, they could watch DVDs and stuff because they came out first with high def. But, you know, for your everyday watching on, you know, cable TV or direct TV or whatever, they were slow in getting high def. Right. And now 4K, same thing. I mean, how many 4K channels are out there? 4K for Sunday football, and then a few of the National Geographic or whatever. But I mean, you can't watch 4K like all the time. Most of it isn't in 4K yet. And so I have two 4K TVs, and it's like, yeah, it's a waste. But that's what, now it's 8K, right? Or do they even have 16K by now? I know they've got 8K.
You got a bunch of Ks.
Yeah. So yeah, it depends, you know, there's got to be an app for IPv6 that everyone, you know, you want to be able to do this. It's going to be business generated. Your company needs to be able to do whatever it is, and it requires IPv6. So we're going to bite the bullet and go there. And whatever we have to update, we'll have to update. Or we'll do the stopgap measures. You know, there's lots of stopgap measures to convert V4 to V6 as it goes out your routers and stuff. And it'll tunnel V4 in V6 or vice versa. Yeah, did you have a question?
That's probably a dumb question, but what prevents these like TV channels from having 4K? Is it like the equipment or?
It's the equipment. Yeah, it takes a lot more bandwidth to stream it.
Oh, okay.
So that means that, you know, for the given number of customers streaming simultaneously, they're going to need more bandwidth from whoever they're contracting with for their internet.
Also have to be shot.
But yeah, besides bandwidth, there's, you know, it's got to be filmed in 4K.
Yeah.
At least. They can, you know, it can be down whatever sized, but And it can be up, like my TV tries to up, like fill in, make it more high def looking. It looks stupid. It actually kind of looks almost like a video game when
It,
it does.
it makes everything look like a soap opera or
It
something.
does, exactly.
Some kind of cheesy
It's, there's a weird move, the way things move when they do that upscaling of with an 80p to 4K.
My father-in-law's a cinematographer. It drives me up the wall. Yeah, absolutely preserved.
I noticed that the first, when I was watching on my downstairs TV, which was at the time the only 4K, I'm like, this looks so weird. And, I look at in regular, on the regular, 1080p and it looks normal. So.
See you Wednesday. Thank you.
Okay, so I think, everyone's brain dead by now, including myself. So